Welcome to part 2 of my proofs of the derivatives of the logarithmic and exponential functions. This is part 2 because in part 1 what we did is we started with the definition of the derivative and we derived the derivative of y equals b to the x and used that to then prove the derivative of y equals e to the x, the derivative of y equals the natural log of x, and y equals the log base b of x. In this video, we'll be going the other direction. We'll be starting by finding the derivative of the natural log of x, and then finding the derivatives of y equals the log base b of x, and then y equals e to the x, and finally y equals b to the x. Well, before we find the derivative of y equals the natural log of x, first let me remind you of a definition that you probably learned about in pre-calculus class, and that is the definition of e, one of the definitions of the number e. The definition that e is equal to the limit as n goes to infinity of 1 plus 1 over n all to the n. You probably saw this in your pre-calculus class when you were studying compounding growth. You first looked at probably compounding monthly, and then daily, and then secondly, and then maybe microsecondly, and you saw that there was a plateau that this went to. And then your teacher probably introduced you to the number e. Well, in this proof, we'll take this as a given, that e is the limit as expressed here. So for now, I will tuck this up in the corner for use later on. And now we'll look at this function here, y equals the natural log of x. More specifically, let's look at the derivative of this. In order to find this derivative, we're going to start with the definition of the derivative. And here is our definition of the derivative. And if we apply this to the natural log of x, the function y equals the natural log of x, we get this, which is that the derivative with respect to x of the natural log of x is equal to the limit as h goes to 0 of the natural log of x plus h minus the natural log of x all over h. Now, before we move forward, if you do not remember all of the various properties of logarithms, you might want to pause this video and refresh them a little bit because I'll be using them a little bit in this proof. But if you are comfortable with them, then keep playing and follow along because I will be manipulating this to get this into a expression that is going to be easier for us to interpret. The first thing I'm going to do is I'm going to combine these two logs into one log using the property that the difference of two logs is equal to the log of the quotient of the two arguments. I'm then going to use some algebra to simplify inside this argument. Next, I'm going to rewrite this here. Instead of the log divided by h, I'm going to write it as 1 over h times the log. Next, I'm going to apply the log property that if you have a coefficient of a log, that coefficient can be raised to become the exponent of the argument of the log. At this point, I'm going to make a bit of a tricky substitution. A bit of a clever substitution. I'm going to let n equal x over h, which in turn means that h is equal to x over n, and that 1 over h equals n over x. Now, in this limit, h was going to 0. So what does that mean about n? Well, one thing in this equation, y equals the natural log of x has to be a positive number. And if h is going to 0, and let's say that h is positive going to 0, that means that you have some number, some positive number divided by some very, very small number. And no matter what this positive number is, if you divide it by a very, very small number, you'll get something that's very large. So as h goes to 0, n would have to go to infinity. And if we make all of these substitutions into this expression, we get the limit as n goes to infinity of the natural log of 1 plus 1 over n to the n over x. Now I'm going to move some of this stuff away. And rewrite this exponent as n times 1 over x. I'm then going to apply the same property of logs that I used before. I'm going to take this exponent, this part of the exponent, and move it down and make it the coefficient of the log. I can then factor out this 1 over x out of the limit, because 1 over x has nothing to do with n going to infinity. Next, I'm going to use a property that you're going to have to take my word for is true, and that is that the limit of the natural log of an argument is equal to the natural log of the limit of the argument. At this point, you'll probably notice something seems very, very familiar. If you notice, right here, we've seen this before. Oh, it's right up here. The limit as n goes to infinity of 1 plus 1 over n to the n is equal to e. So let's make that substitution. And we know that the natural log of e is 1. Therefore, this entire expression that we started with this thing up here will all simplify to 1 over x. So that is the derivative with respect to x of the natural log of x is equal to simply 1 over x. This connects natural logs, and all logs in fact, with rational functions. And if you watched my first video about the derivative of exponential and logarithmic functions, we proved that the derivative of the natural log of x was equal to 1 over x in a completely different manner, using a different definition of e. And what that means, if we already know that the derivative of the natural log of x is equal to 1 over x, that tells us that this part here must in fact be e, because this whole thing has to be 1. And the natural log of what number is 1? Well, the natural log of e is equal to 1. So this would have to be e. So the other definition that we saw in the first video then implies that this definition of e has to be true. And if you want to know that other definition of e, I'll either give it at the end of this video, or you could watch that first video I made. We'll now use this derivative as a known fact that'll help us to prove very quickly the derivatives of those other functions mentioned at the beginning of this video. The first being the log base b of x. Now, in the first video, I proved this in a very different way. So there's a couple different ways of proving this, but with the knowledge we know now, the easiest way is to rewrite this y equals the log base b of x using the change of base formula, rewriting it as the natural log of x divided by the natural log of b, which we can then use algebra to write as 1 over the natural log of b times the natural log of x. This is convenient because what this is, 1 over the natural log of b, is a constant. So we have a constant times the natural log of x. And its derivative, if we take the derivative of both sides with respect to x, the left side becomes dy dx, and the right side becomes 1 over the natural log of b, the coefficient, times the derivative of the natural log of x, which is 1 over x, which is more commonly written as 1 over x times the natural log of b. The reason why x is written in front is because otherwise it might get confused for being part of the argument of the log, and it's not. It's x times the natural log of b on that in the denominator there. All right, so that is our second proof. We'll now add this up to the top here as our list of known derivatives. And the next one is one of the coolest ones. It's one that mathematicians really appreciate, and that is the derivative of y equals e to the x. Well, at this point, we don't know how to take the derivative of this, but what we can do is rewrite this equation into an equivalent form. Y equals e to the x is the same thing as the natural log of y is equal to x. These are equivalent equations. And what's nice is, although we don't know how to take the derivative of the first one, unless we watched part 1 of this video, but we do know how to find the derivative of the second one. We can take the derivative implicitly with respect to x. The derivative of the left side, the derivative of the natural log of y, is going to be 1 over y, 1 over the argument, times the derivative of the argument by the chain rule, and the derivative of y with respect to x is dy dx. On the right side, the derivative of x is equal to 1. If we then solve for dy dx, we get that dy dx is equal to y. And we know that y is equal to e to the x. So that means that dy dx is equal to e to the x. And this is a pretty amazing thing, that the derivative of e to the x, if y equals e to the x, its derivative is the same thing. The derivative of e to the x is e to the x. And now we can add that to our list up here of the three derivatives that we now know. And the last one we want to look at is a generic exponential function, y equals b to the x. And just as we did with the last proof, we can rewrite y equals b to the x as the log base b of y is equal to x. And this is an equivalent equation, because b to the x would equal y. The base to the answer is equal to the argument. So these are equivalent equations. And this bottom one here, we know how to take the derivative of. If we take the derivative with respect to x, well, we know that the derivative of x is 1. And to find the derivative of the log base b of y, we can apply this property, this equation that we already proved. And we'll arrive at this. And again, this came from applying this property. The argument here is y, so you have 1 over y times the natural log of the base, and then times the derivative of the argument, the chain rule, and that's equal to 1. If we now solve for dy dx, we get that dy dx is equal to y times the natural log of b. But we already know what y is. Y is b to the x. Therefore, we can finish this off by saying that dy dx is equal to b to the x times the natural log of b. Which is the final of our 4 derivatives. So the derivative of the natural log of x, the derivative of the log base b of x, the derivative of e to the x, and the derivative of b to the x. Now in this video, we proved this one first using the definition of the derivative, and then quickly used it to prove this one, and this one. In part 1 of these videos, I started by proving this. The derivative of e to the x is equal to e to the x. And from there was able to prove the derivative of b to the x, the derivative of the natural log of x, and the derivative of the log base b of x. And these arguments are not circular, which is kind of neat. So if you're curious of how to go prove these a completely different way, then watch part 1 of this video. If not, you now know where these can come from, and if need be, you could prove them again. But it is important to be able to prove these from each other, because if you know any one of these, you can actually prove any of the other 3, which is kind of neat. So I hope you found this useful, and hope you tune in to watch more videos as I make them. Thank you very much for watching.